about Asio, really. So the asynchronous I/O library, the whole Flash XML thing came up very similar to why the Spirit discussion came up yesterday. Spending time on IRC, I started using the asynchronous I/O library some time ago, and really liked it a lot. Got rid of all my own stuff, converted to that. People were asking questions on IRC, nobody was ever answering them, and I thought, huh? One way to learn is just start answering questions. So a lot of this presentation comes from what I've learned from helping people on IRC with the asynchronous I/O library, which again means it's pretty tutorial-like for a presentation. So let's get started. Asynchronous I/O library. This library started off as a network library. That was the intent, and it's kind of grown from there. It uses a proactor model, which we'll talk about and what that means. But in essence, it's a very efficient way to handle lots of things going on at once. And so we want to be able to handle lots and lots of connections. It grew from that. It doesn't just handle network activity anymore. It's got serial ports, file descriptors, timers. It's got all kinds of things. The library is large, and the reference though is very good. So if you're going to start with the asynchronous I/O library, I recommend reading the first part, the overview that everybody always skips, because it has all of the nuggets that are really important in it. So if we miss them here, we'll get them there. Yes?
Still implemented in headers?
Excuse me?
It's still implemented in
It
headers?
it is primarily header, though there can be a dependency on thread and on system. So those you'll need to link. But let's not worry about that for now. All right, what is asynchronous I/O? So I have a number of kids. My oldest two daughters are great. I work from my home office. I say, hey, I'd like to have a coffee. And my oldest daughter says, great. And she runs on down, and she begins to make my cappuccino. I sit there, and I continue to work, and I get stuff done. Eventually, she comes upstairs. She hands me my coffee. I say, thank you. That was an asynchronous transaction. Very excited, right? I got a bunch of work done. I just made a request for a coffee, and the coffee came in. My third daughter loves to make coffee for me. But the problem is she needs supervision. She needs the type of supervision where I watch her make the coffee, because that's the fun part, is making the coffee. And so I'm not actually allowed to help in the coffee making process. I'm just allowed to stand there and make sure it doesn't go awry along the process. So the end result is I ask for a coffee, she gets excited, she wants to make me a coffee. We both go downstairs, we hang out at the machine, she makes it work, I sit there and wait. She gives me my coffee, I say thank you, I go back upstairs, I sit down. That is not an asynchronous type of mode to get coffee, all right? I sat there, I made a request, I sat there and I just waited for the thing to occur. Oh, you can sit anywhere you like, Marshall.
Probably not true, since it's all the chairs are full.
That's true. If you sat there with the projector, that would be bad too. But, what might look like in code? You have some function here called read file. It takes a file name, it takes a buffer, and it takes a handler to call when it's done. It goes on, so it starts the process of reading the file. It doesn't wait for the file to get read, it just starts that activity. It goes and does some work, and eventually the handler gets called saying it was done doing that. Now, if you're thinking a bit at the moment, you're going to say, well, wait, I've started something someplace. Later, likely in some other thread, I'm going to get notified that it occurred. This is going to sound like it's going to start getting a little complicated. And so you might ask, and at this point I was going to scare you for a little bit, but I'm not going to do that or else we won't get to the end. Sounds hard, so why? So let's just think about maybe one of the reasons why we might want to do this. So you have a server and you have a client, and you're naive. So if you're naive and you have a server and a client connects, you need to read data from it, but you don't want to block reading data from it. You want to do something else also. So what do? You create a thread. The thread is going to sit there and block on the read, and potentially you want to write data back out. Depending upon how sophisticated you become, you might want to create a write thread and a read thread for each. Or you might be a little smarter, you realize you could have one write thread that's going to handle all your clients, but they still each have to have a read thread. As you can see, this is not going to scale very well for us. We've got 4 clients, we now have 8 threads, and at some point you're going to become pretty unhappy. If you're not, your customer is. Somebody's going to get really unhappy with all the resources just sitting around doing nothing. We would prefer something like this, an asynchronous model. We have lots of clients connecting, but we're able to service all of them with one thread. Because think about it. In this past slide, what are we doing most of the time? We're waiting, right? We're doing nothing. We're wasting resource. We're just kind of hanging out. All right. I'm not sure about you, but for me, as Hartmut knows, because occasionally I'll tell him that my world view of spirit just got adjusted. I have mental models of how things work. It's not how it necessarily works, but it's my mental model of how it works. I'm just a user, right? And as long as that goes well in life, I'm happy. As soon as it breaks, I'm just like the physicist who tries to figure out how to change my model slightly, and then I have a new model of how the world works. Because I really don't care necessarily how it all works. I just need the right model. This seems to be the hardest part with the asynchronous I/O library. If you're not familiar with a ProActor model and you have never used one before, and you're coming at this without maybe visiting a reactor model either, which would be like an ACE, then you need to get some adjustment. And so how we're going to get some adjustment is we're going to have a story. So, reading slides is bad, but reading stories is good. So, I'm going to read you a story. The story came about because my wife, who is an art major, said when I showed her my slides and I was very excited about Beamer, she said, "Those are boring." So, we're going to try to spice them up here. So, this is a ProActor story. All right, Mom, Dad, Johnny, and Butler, they go to the beach. Dad tells Butler to wait at the slushy shack. After some time, Dad and Johnny go to get a slushie. Dad brings his own cup. He is greeted by the owner. "I would like to order a slushie. Here's my cup. Please deliver it to Johnny when it is ready." Dad heads off to explore the beach. Johnny builds a sandcastle. Owner begins to make a slushie, and Butler waits. Owner starts the blender and goes back to take the next customer's order. Ding! Slushie's ready. And owner moves the cup to the completion table where the assistant is waiting. Assistant gives the slushie to Butler for delivery to Johnny. Butler's happy to have something to do. Butler delivers the slushie to Johnny, who's happy too. Butler returns to the slushie shack and waits. Dad sometimes will order multiple slushies, one for Mom and one for Johnny. That isn't a problem. Assistant just gives the first one ready to Butler. Butler can only deliver one at a time and returns for the second slushie. Other families come to the beach and bring their butlers, who also wait in the slushie completion line. This works well because it helps keep the assistant's slushie completion table empty. Assistant still remembers that fateful day when no butlers came to the beach. There was also the time that each kid brought a butler. Disaster, no room at the shack. Too busy, yet nothing was getting done. The families agreed that 2 butlers would be plenty for all. Now they share. Occasionally, tragedy strikes. Johnny will leave to chase waves without getting his slushie. Butler will die of exhaustion trying to find him.
You knew it was a dangerous job when you took it.
Or somebody will take their cup and go home while the slushie is being made. Then it gets poured all over the floor. Yuck. Dad is sometimes very generous. Johnny would like an orange and one purple slushie. If both slushies are done at the same time, and both butlers are available, then Johnny gets 2 slushies at once. This confuses Johnny and causes brain freeze. Susie is smarter and doesn't mind if both slushies come at one time. But most of the time, the dads are making requests to the owner, the assistant is monitoring the table, the kids are building sandcastles, and the butlers are just waiting. All right, let's go ahead and take a look. Sadly, the proactor model is not as creative, and they use very boring names. So Dad is called the initiator. The butler is kind of the proactor. I've taken some liberty here, and I'll tell you what that is here in a moment. The asynchronous operation processor is the owner. An asynchronous operation itself was the blender actually making this. Asynchronous event demultiplexer is the assistant. There's a completion event queue, which was really our completion table, and then there is a completion handler, which was Johnny. We had some additional roles played today. The operating system was basically the blender. Memory to be filled was the empty cup. The slushy was the stuff filled in, so a full cup was the data in the memory. This is the very boring thing we would have normally drawn and I would have talked about for a long time. But hopefully that story just told us all of the different relationships that exist. What I would like to mention here is where the asynchronous I/O library exists and where the rest of our stuff exists. And so Dad, who is the initiator, who's starting the asynchronous activity, that's our application. That's part of our stuff. The completion handler, that's part of our stuff. The proactor, notice we supplied the butler when we got to the beach. The top half of that, the thing that's going to deliver it, is our part. The bottom part of the proactor actually belongs to the asynchronous I/O library, and we'll talk about that in a little bit. Okay, a few lessons hopefully from the story. Everything that was happening inside the slushy shack, all activity, all threads, anything that was going on in there is completely transparent to the families at the beach. They don't really know. They make requests, and somehow through the butler, which they supplied, they get the thing back. But whatever else happened inside the shack, they don't know about and they don't care about. Second, the butler delivered the results. And the butler was supplied by the family. So the result didn't come from the shack or from the asynchronous I/O library or from the proactor model. The reason you got it was because you gave it something, a thread, to deliver it to you. The cup was both supplied by the family, it's owned by the family, and if the family takes it away, we're going to have problems. How many are familiar with the ACE libraries and using that? So the ACE, primarily, I haven't used ACE for a really long time, but primarily ACE is a reactor system. They have a proactor, from my understanding now, built on it. One of the main differences between a reactor and a proactor is that in the reactor, you don't supply the cup, you're told that the thing's done, and then you supply the cup. So you can see there's going to be some memory that we're going to be giving away, and it's going to be hanging out in the shack. We're going to be having cups hanging out in the shack until something's done and we get them back. That could be considered a disadvantage of this model. A few more. Some handlers, like Johnny, don't like to have multiple things delivered at once. I think this is where I'm supposed to say use locks. So Susie, she doesn't care. So Susie uses locks. Johnny doesn't. For whatever reason, you write the handler, you own Johnny. If you make Johnny so he can't handle multiple things being delivered, then keep that in mind. Don't leave the beach with your cup before you've gotten the stuff you're supposed to get. That's the same thing as having some reference call that isn't there anymore, or a pointer that's being filled up with stuff that's been deleted. It's a bad thing. I'm sure you've all had bad things. It only takes a few butlers or a few threads to handle all the requests that are going on in the system. And that's really one of the keys. You don't need a lot to service a lot of activity that's going on, because I/O is slow. And that's the whole idea, right? You've made a request, now you're just waiting around for it, so instead of waiting, you're gonna go do something exciting. But somebody else is gonna wait for you.
On the previous slide, why don't we have a notion of cancellations, so we can link the bitch?
You can. So if you canceled the blender, you could leave them. Yeah, you're right, it cancels the request.
It cancels the shack.
And that, you tell the shack that you want to cancel the request. And then what it does underneath, there's some different things that occur. So yes, you could do that. You could cancel your order. Most people don't. Especially if you're starting, you're more likely to leave the beach without thinking about canceling. And you'll probably do it on accident. We'll talk about how you get around that. Okay, let's look at some examples. We're going to use timer at first. Timer is one of the facilities that's inside the asynchronous I/O library, but everybody understands a timer, and this is going to be really easy to breeze through and just start understanding some of the basics of this library. Right, so I've created some function called timer expired. It takes an error code. It's going to print out timer expired. Inside of main, I'm going to create this thing called the I/O service. This is the shack for all practical purposes. And the I/O service is the pro actor.
Yeah.
It's also a bunch of the other bits, but think of it at the moment as the shack. We'll refine our thoughts as we go, but this is a good place to start. We're going to create a deadline timer. A deadline timer is going to eventually become a request. It is the asynchronous thing that we want done. And we're going to eventually make a request on that asynchronous thing to have it done asynchronously. The Asio library can do synchronous and asynchronous. We're not going to talk about the synchronous stuff because it doesn't interest me at all. So we're going to only talk about asynchronously. All right, so we create this and we tell it that here is the shack. So we tell it where the I/O service is, and we're giving it a timeout period. This one is related to 5 seconds. So we have a deadline timer. It's going to expire in 5 seconds. Now I haven't started it yet. We made one, right? So it's like the order tag. We haven't given it to anybody to make the request, but we've got the tag. Here we're going to start it. So we say timer async wait, and then we give it the handler. We tell it, who do we want you to tell? This is Johnny. We want you to tell Johnny when it's done. So timer, we're using the timer object, and the async wait, at this point, we're making the request to begin the wait. All right? So for 5 seconds. We're going to just print out calling the I/O service run. Here's the I/O service run. This is like supplying a butler. All right? You don't call run. Remember, cups line up on the table, nothing gets done. So this is the thing that is going to call the handler. And then we're going to have printout done. Let's see what happens. Yep. Go ahead.
Okay, if you go back one slide,
Yeah.
when does the timer actually start? Or the
Just
actual
like
time frame?
yesterday, I tried to anticipate everybody's questions, and it's the very next little slide. Do you have a
Well,
question?
that's pretty much the same question. I just wanted to understand, there's two commands in line 14 and 18. You said that the command starts in line 14.
Well, you'll see in the next set, and everybody asks this.
Where's actually the operating system thread created to run the timer?
There is no thread in this created.
I mean,
As far as your, I don't know,
Okay.
right? We don't know, we don't care.
Well,
This is part of what occurs in the shack we don't care about.
because normally I have to associate the thread with the I/O service. No?
So you,
No.
we will finish, I think, in
Later.
our next set of slides, it'll become a little more clear what's happening. And then, if not, you let me know. Okay, so what we have here on the output, calling IO service run. Right here, calling IO service run. Timer expired, this was our handler got called, and then done. Done. We'll talk about this later, why we did the done. Okay, we're going to hold off on that. All right, here is same thing. Same timer, but now we've got this little thing called now time. Now time is just going to print out the current time in second, with second accuracy. Okay, it's just date with time. So nothing is new at all, except for a couple more print statements. Here, we're going to let us know when we're making the request. Here we're going to see that we're going to sleep for 3 seconds before we come down here and say that we're calling run. We make the run call. So now, if the timer starts here, when the async wait is requested, we would expect from this point 5 seconds to the time that we get the timer expire call, right? If what's occurring is it's not until we call this Asio run, then it's going to be 5 seconds after this time. Make sense? What we're trying to show here? Okay, so what we get is request for async wait for 5 seconds. This is at 13 seconds. The sleep occurs. We're going to call run 3 seconds later as we expected. And at 18, the timer expired. So that means the timer started at the request, what we expected. Just like Dad going and making the request to have a slushie made, the slushie gets made right away, right? It's being made. It gets put on the completion table, but if you didn't supply the butler, it's still there, it's still done, it's still made. It's just sitting on the completion table waiting for somebody to deliver it. And the person who's going to deliver it is whatever thread called run. We doing good? All right. So we're going to just take a moment and we're going to go through bind. And if you read what this talks about, we're going to go through a couple different libraries. Yeah. Dean.
Can you go back one
You
slide?
bet. One more or?
Yeah, that one.
Yes.
So we still get to the done part, right?
Yes, but we're going to ignore that at the moment.
Okay.
Why we're at done.
All right.
We're going to fix that.
So okay.
Yeah. You've used the library?
Yeah.
Okay. If you've used the library, don't explain why we got to done yet.
Okay.
We'll take care of that. So last year at Boostcon, one of the things that I learned was, it was my first year, that the audience here is pretty large. You have authors, you have power users, you've got people who have a couple libraries that they know really well, and then you've got the rest of us mortals who just like move along and use what we can, and we know certain libraries and we've never even heard of the rest, right? And the reason you know the library you know is because it solved something and then maybe it needed another library and so forth. And so last year, personally I was a little surprised at the number of people that didn't know bind. And so I thought we'd just go through bind in case there's some people here who don't know bind. The idea is, here we're going to have a function we're going to call divide. It's going to take two integers. It's simply going to return the first argument divided by the second argument. Okay, simple enough? All right. Here is the bind call. And the intent, what we want to do, is we want to bind something and create a functor, a function object, that later we can then invoke and have it call the thing that we bound to. All right? And we're going to go through a couple of examples so that it'll all make sense and I won't have to try to describe things. So I'm going to bind to divide. I'm going to use placeholders. _1, which will be the first argument when I make the call. _2, which will be the second argument when I make the call. This here, this bind, has now created a functor. There's an object here. I'm going to now take that object and I'm going to call that object, the functor, with two arguments, 10 and 5. The result then, of course, is 2. To be honest, when I learned bind, and I kept seeing this over and over in the documentation, at first it confused me. So this doesn't confuse me when I first started. We're going to use something that we'll just ignore at the moment a little bit, but boost function. It has a signature of it's going to return an integer, whatever this function thing is. It's going to take 2 ints. And we're going to bind the functor to that, and then we're going to use it. So for me, separating the two steps made more sense. So here we're going to bind the exact same thing, and now we're going to call it func 10, 5, and then we're going to get 10 divided by 5, which is 2. All right. We could swap the placeholders if we wanted. It doesn't care. So here we're calling it with 10 and 5, but when we bound it, we bound the placeholders so that they're opposite, and now, even though we're calling it 10 and 5, we're going to get 5 divided by 2, which we're doing integer division, which is 0.
By 10.
Thank you. Paying attention as well. We could also go ahead and not just bind placeholders, we can bind actual values. We can bind them in the order we want. We can have a whole bunch of things. So here, we're binding divide with a 20 and whatever the fifth argument is. And then when we call it, we're going to call it with a whole bunch of stuff. Well, we only care about the fifth argument. So only the fifth argument is going to make it. And so now we have 20 divided by the fifth argument. We passed in 6, so that's 2. And we're going to get 10. All right, moving on. We're going to use now an add. And we're binding add with a 20 and an x. So we can bind a variable. So when we call this, we're going to end up with, that is, right here we're going to call it with no arguments. Why did we call it with no arguments? Because we don't have any placeholders, right? So when it gets called here, we're going to end up with 20 divided by, what was x? 5.
Add.
Add. Wow. So, I've had a cold and I took 2 Sudafed right before I came. It might have been a bad idea. All right, moving on. Here we have our x, 5, 20, just like before. And now we assign x to 10. We call our func, and we get 25. So, the last time I looked, that's not going to work. 20 plus 10 is 30. So what happened? Well, what happened was, bind makes a copy. So the copy of x at this point was 5. And so we're actually getting 20 plus 5 and not what we wanted. How do we get what we want? We use boost ref. So now we're supplying it, we're wrapping our variable inside of a reference. And the end result now is what we wanted. It's our 30. When this occurs, it's going to use a reference to the x, which is going to get us our 10. Yes?
Can you actually go back to the last slide?
The last slide.
Yeah.
This.
No,
The last
yeah.
slide.
Yeah, right here. I
Mhm.
thought when you do a bind and you say underscore 5, that creates a function of 5 arguments.
No. Underscore 5 just means it's going to take the fifth argument at call time.
Right, but the bind function, once it executes, the functor that it creates, of how many arguments is it?
Well,
It takes at least 5, but bind will actually drop more on the floor. It's a bind implementation
Well,
decision.
it's an implementation detail,
Yeah.
but I thought that was just an implementation detail from a specification you weren't supposed to log.
No, bind is
yeah.
supposed to drop extras on the floor. It's
So it is
considered
actually
useful.
legal. Okay.
This is boost bind, by the
You can
way.
have-
It's the
Yeah.
one I know.
I believe std bind works,
Yeah.
gr1 bind works the
So
same
it's
way.
implementation side effect.
Can I point out that if anyone finds bind confusing, if you have a compiler that supports lambdas like GCC45 or VC10, lambda supersede 99% of uses of binds. And they let you write normal SQL spots, but it's a different way.
Yeah.
Is that also true when you use Asio?
Yes, yeah, like Asio I assume doesn't care what functors you give it, so
Yeah.
bind is just a convenient way to create functors, so it'll accept built-in lambdas as well.
That's cool.
Okay, now we're going to bind to a member inside of a class, to a method inside of a class. So we have this class adder. Adder is going to do nothing more than, inside of its functor, take 2 integers, add them together. I guess actually we don't use the functor, so never mind. It's got add. Add takes 2 integers. It's going to add the 2 numbers, store that in last, and return last. So here is what bind looks like. It's the address of the method we want to call. We have then the object, and then we have our placeholders. Voila, it works just like we want it to, except that we got back 24, but it thinks, if I pull out last, it thinks last is 0.
And you made a copy.
Exactly. You guys are so smart. So I made a copy again. If I use reference, I get exactly what I want. The other option is I could have actually passed an address
Yeah.
instead. Okay, that was our bind tutorial. Moving on, now we're going to use bind. So, we're going to create 2 timers this time instead of 1. One's going to go off in 5 seconds, one's going to go off in 3. When we do the wait, we're going to bind the callback. So we're going to bind the handler, same handler, but this time we've added an identifier, a string identifier as the first argument, and the second one that we're still kind of ignoring at the moment. So here when I use bind, I'm going to give it the handler. I'm giving it as the first argument, timer 1, this one timer 2, and then _1, the placeholder, the first placeholder, which happens to be this error code. So, where's the error code going to be coming from then? Asio. Okay, we're going to print out run, and then we're going to go run it, and voila, it does exactly what we thought it should. Timer 2, which was only 3 seconds long, went off first. We got timer 1. All right, let's do the same thing. Let's introduce a thread. We're not going to talk a whole lot about threads, but creating boost thread, it's easy to create a thread. Here, boost thread. It's going to be called butler. We've got one. It's the object. And then we're going to bind to that what it is that we want to have run in the thread. So the signature of whatever we're passing to the thread in the constructor is basically a void. And if you want to do something with it, you better go ahead and bind, or else you're not going to be able to pass something into it. So what we're going to do is we're going to call, in this case, remember with our bind, here's the Asio IO service run, and we're going to pass it then by address, the actual service itself. Down here, butler join. What this does is when the thread is done running, when it's completed its execution, this will then return. So it's waiting for the thread to return. We've added a sleep up here of 3 seconds. And now let's see what happens. All right, timer 1. Oh, let's verify here. 5 seconds and 5 seconds. They're both going to go off at the same time. All right, both slushies will finish at the same time. Timer 1, we enter it, and then we leave it
3 seconds later.
3 seconds later, like we should. And then timer 2, as soon as this one was done, gets delivered, and then it expires. So I kind of lied in the story where the butler went back right away. Well, the butler hands the Slurpee to the kid, Johnny. Now, is it about what Johnny does with it? You know, he might have to wait around for Johnny to drink the Slurpee before he gets to go back to the shack. And that's basically what happened here. He's having to wait 3 seconds before he can now go back and handle whatever else is on the completion queue. Make sense? Okay. Let's use 2 threads, because 2 is better than 1. Everything else is the same. We're now going to use this thing called a thread group. And then we can take whatever the object is and call create thread. We're going to bind our run again. And now we're basically running twice. This is like supplying 2 butlers to the slushy shack. Okay? And now we're going to use on the pool join all. So now what do we get? Well, timer 1 went off at 49, and timer 2 went off at, timer 2 went off at 49 also. They waited 3 seconds, and then they completed. So both of them are occurring at the same time. That's what we expected. Both timers went off in 5 seconds. All right, post. Post is as if the owner of the slushy shack got an order which he could service immediately. He got the order and whatever it was, just goes on the completion queue. It just needs to be delivered. He gets what has to be delivered. Okay? So dad comes and says, hey, can you give this ball to Johnny? Not a problem. Owner takes the ball, puts it on the completion table. As soon as there's a butler available, the ball gets delivered to Johnny. How we do this is we take the IO service and we call post. And then we just bind a functor to whatever we want to do. So we're going to, we have a function up here, which is going to simply print whatever it gets. And so we're going to have do work is what we're binding, and then eat, drink, and be merry. we create a butler to run, we run it, and we get eat, drink, and be merry. So eat, drink, and be merry got called by the butler pulling off the first one, eat, delivering it, drink, delivering it, merry, delivering it.
Are you sure to get them in those order?
If you are sure to get them in the post order. Well, let me rephrase that. You're not guaranteed to get them in the post order unless you use what's called a strand. And we'll talk about strand in a moment.
Or have one thread.
Or have one thread. But it's still not a guarantee.
Or have one thread
The
posting.
asynchronous IO library does not guarantee the order of delivery unless you use a strand. In practicality, with the implementation, you're going to get them in order.
Yeah.
Next, we should do this one. All right. We're going to do something a little bit different this time. So we're getting excited now because now we know how to post things and we know how to create timers. So we're going to create a timer. It's going to go off in 5 seconds. Timer expired. Just going to print out the time. Timer expired. We're going to create our one butler, one thread, right here. So it starts running. And now, in this loop, we're going to go ahead and call post, do work, and we're going to give it the value. So up here, it's just going to say do work, and it's going to print out the time and what work and whatever value number it's on, right? So 0 through 9. And then we're going to sleep 1 second. So post some work, sleep 1 second. Post some work, sleep 1 second. So we've got a couple requests sitting there, right? We've got a timer request that's going to go off in 5 seconds, and every second we're posting something. All right? This is what we get. Work 0 through 4, timer expired, done. What's going on? I mean, it would be nice if we got work 0 through 9, timer expired in the center, because that's kind of what we thought was going to happen. So, lie in the story number 2. All models are broken. But it can be easily fixed. So this is how it works. Butler goes to the shack, and he says, hey, assistant, do you have a slushie for me? And he says, no. But not only do I not have a slushie for you on the completion table, the blenders aren't doing anything either. Why don't you just go home? Okay, so if there's nothing to be done, if there's no work being done inside that's going to be pending for completion, and there's nothing on the completion table, the thread will end. Well, that's pretty inconvenient if we want just to stick there and keep working on stuff.
Mm-hmm.
So what we do is we create something called
Work.
a work object. So we're going to create this work object. We're going to new it. We're going to give it the service. And then at the end, we're going to delete the work object. We're going to tell it, we don't have any more work for you to do. We're going to delete that object. So let's take a look at what we have going on again. Same exact stuff here, same exact stuff here. We're going to queue up in very little time all of the work to be done, and then we're going to delete the work object. But that's okay. So, let me back up and rephrase that. So what happened before was the timer was sitting inside the queue, waiting to be done. 5 seconds. We were posting once a second something that was going to occur. The timer completes. Let's say the post now completes. We wait 1 second, there's nothing to be done. Threads in. Make sense? Okay, now what we've done is we've created this work object, and that allows us, until we get done queuing up all the work we want to be done to complete, it's going to hold on to that so that it's not going to be finished. So it looks like there's a blender doing something. It's not really doing anything. It's just a way of us telling it. So now we're going to get them all, because there's that work object.
So the work object has to be on the table, or can it be on the stack?
So the work object can be on the stack, but if you want to get rid of it at some point,
So you put it in a
In the
scope,
scope.
probably.
you can get rid of it in the scope. There's all kinds of ways you can do this. Yeah.
I'm
Yes.
unclear on the rationale for the behavior of, if you go back a couple of slides, you got to, the timer went off and things stopped.
Right.
Why does it behave that way?
It behaves that way because if you recall in that original diagram of the proactor, requests are coming in, and they're actually getting stuck in this request queue waiting for things to get done. There are things in the completion queue waiting to get passed out to whoever the handler was. And if there's no work to be completed, then the whole service is not serving any purpose. And so by default, it just goes away.
Well, to me, it seems like a producer-consumer problem, right? At least that's how I'm thinking of
Yeah.
it. Right, so you
yeah.
have a consumer who's waiting for something to be put in the queue.
Right.
And it's going to wait and wait and wait and wait until something gets put in the queue and then consume it.
Right.
And that's not what's happening here.
Exactly. So in order to do that, you create a work object. And so.
But when is this behavior useful? I guess that's what my question is.
Yeah. Okay. Good question. And actually, I think we'll get to it here in a moment. But let's just talk about it for now, and then we'll see it even again further. Let's say you have a client that's connecting to a server, and what you've done is you've created an object that's going to deal with the connection to that server. When that connection goes away, you want the client to go away too. And it may be that it's a temporary service that you're providing, and you just want the whole thing to go away when it's all done. It's a one-time service that you're providing, or a one-time activity, or a one-time set of asynchronous activities that you want to occur. I have a thing where I have some serial communication going on, and it needs to happen at the beginning of this certain activity of power up. But after that, I don't need it anymore. And so actually that's controlled by one of these. I don't give it a work, I give it a work object until I give it all the work that I want it to do. And then I kill the work object, and then I know that resource is just going to disappear because I don't need it anymore later in the lifetime of the project. So I think you can make the argument that why, right? It's a producer-consumer, maybe it should just stay there all the time. But you have the ability to keep it there all the time by creating a work object. And if you don't need it, then just get rid of it. I think that's the boost way anyhow, right? During the review process, somebody comes up with something that's just like wacky, and you say, okay, yeah, okay, have this work object. Was that, did I say another thing? D?
Well, I was just gonna say that the run function will actually return once your queue is empty. That's really what happens. So there's a condition it's waiting on. If it's empty, it returns.
Yeah, because
So it doesn't matter if you keep adding after the run returns. Actually, if you call run again, then it's just gonna finish off what's in the queue again.
Right.
Because in most cases there's also no way to insert any new work to do once there is nothing in the queue.
Yes.
Because unless you pass a reference to the other service somewhere else.
So your work object
This is a
actually
it's a
becomes
common way to do,
sent
for
in a-
example, distributed state machines. You've got machines that are communicating to each other. As long as there's stuff inside of the message passing queue, there's still work to be completed.
Yeah.
But as soon as the queue's done and empty, the state machines in essence have nothing else to do, right? Unless there was a timer hanging out, there's really nothing left for that machine to do. The machine should just die. And so that's kind of a normal process with, I think, state machines also, but not for producer consumer. All right. Okay, here I've gotten rid of the timer, or excuse me, the delay that we had up here, so we're not going to wait anymore. We're going to say we've entered, now we're leaving. We're going to have two timers. They're both going to go off in 5 seconds. We're going to have a pool that's going to have 2 threads, so 2 threads waiting to hand out things. They're both handing out because we've bound the completion to be timer expired. They're both going to hand their results to the timer expired. So, in theory, this is the slushies both got made. Slushies are both ready to be delivered. Johnny can't handle it, right? Johnny can't handle it. So we can actually see that we have both threads inside of the same completion handler at the same time. We're kind of getting stuff printed on top of each other. So if you're Johnny, this is going to make you sad, right? If you're Susie, you were smart enough, you know how to handle both of them at the same time. So what do we do about this, other than locks? We're going to create what's called a strand. And for some reason, once a month, somebody comes on IRC and asks why it's called strand. I don't know. Okay.
But that's why your example story on the beach, right?
Right. Yeah. Thank you. Yes.
A thread consists of multiple strands. Right?
That I tried that. It didn't go anywhere on IRC. Maybe it goes somewhere here, but.
Well, actually, if you wanna tie all your handlers into a single order, you need a strand to do it.
We're gonna do it, but I don't know why strand is the name. So.
No. So you use the strand to
Use
tie
the
them
strand.
together.
So what? This all looks the same as what we've had before. This stuff right here, right? This is exactly the same. We've seen all this. Here now, what we've created is a strand, and we've given it our I/O service. Everything gets the I/O service. We've given our strand the I/O service. Now what we've done is we're doing our bind as normal, but we've wrapped it inside the strand. Wrapping inside of a strand guarantees that objects that are wrapped in the same strand will not execute the completion handlers at the same time.
So you give
It
it
does
an
not
order.
guarantee the
Order,
order,
yeah.
but it does guarantee that two won't occur at the same time. There are guarantees about order. I point you to the strand documentation page in Asio. There's a long description about a bunch of rules.
Does it guarantee also that it is handled in the same thread?
No, it does not guarantee that it's handled in the same thread. So here we have two threads running.
Yeah.
Both are waiting at the completion queue, right? One is going to grab a result and take off with it. It's quite possible that the other one is going to grab the other result, but he can't actually deliver it until the first one returns. That's all the strand tells you. So they may be delivered by different threads, but they're not going to be delivered at the same time. All right, we do it now, and timer 1 enters, leaves, and then timer 2 enters and leaves. Okay, so we've gotten what we wanted. We've serialized at least two things. So had I went through and modified some of my slides at this point, from now on till the end of the discussion, I would keep saying, use a strand. Okay, it's like use a lot, use a strand. They'll say. Shared pointer. Quick introduction to shared pointers if you don't know what they are. So what we're going to do with the shared pointer is we're going to take something that we've newed off. We're going to give it to the shared pointer. It's going to wrap it, and then we're going to use it like it's a pointer. But when we make copies, we're going to get some reference so we know how many are hanging on to this pointer, and they're going to increment. And then when they go away out of scope, they're going to decrement. And eventually when they go back to 0, we're going to delete the thing we own. Right? So we're going to do lifetime management. So here, entered scope, we're going to new off this new printer. We're going to tell my printer to print an 8. We're going to leave the scope, and we're going to print that we left the scope. And we get entered scope, printer created, we print the 8, we're leaving the scope. Here the printer is destroyed, and we print that we've left the scope. Okay? I think everybody probably knows shared pointers. Less people may know actually enabled shared from this, unless you already use the asynchronous I/O library and then you use it all the time. So what we're doing here is we've created now a shared printer, and we're inheriting from this thing called enable shared from this, providing it the name of our class. What this is going to do is, all this rest of the stuff looks the same. We're going to add a method called getPrinter. It's going to return one of these magic function things that has a signature of void int. And what we're returning is we're going to bind to the print. And instead of this, which we saw earlier when we were binding things, or a pointer or an object, we're going to use this shared from this. And so it's not just this, but we're going to have a shared pointer to our this that we're going to bind. And then whatever that first argument is. All right, we have two scopes now. Entering first scope, we're just going to create our print. We're going to create our function object out here. We're going to then enter scope 2. Here we're making our my printer with the shared pointer. We're going to call it like we were calling it before. Then we're going to go ahead and call this get printer and assign the result to print func. So that's this thing, right? The shared from this. So here at this bind point, we now actually have a shared pointer here, and we have a copy that has occurred through the bind. And so we now have two reference count, right? Reference count of 2. Leave scope, left scope. We're going to now use it, print 42, leaving scope 1, left scope 1. And so what we get is enter scope 1 to scope 2. The shared printer is created. When we leave the scope, it didn't get deleted, which is what we wanted. We then used the func, and then as we left scope 1, when that went out of scope, the function object went out of scope, then the shared pointer was destroyed. Okay, this is going to help us keep the people on the beach that we want on the beach.
So I have a question, pretending that I haven't used shared pointer before.
It's a really long presentation. Mr. I've never used shared pointer before.
Pretty dangerous. So I guess I get, if I hadn't used shared pointer before, why I couldn't just say this there, because then the thing that I store in the bound functor in the boost function wouldn't keep the printer alive.
Yes.
But why do I need to use a shared from this thing? How come I can't just say construct shared pointer from this pointer?
Okay, so what's shared from the short and I'll give you a short, hopefully succinct answer. What enable shared from this does is it actually creates a weak pointer as a member. So at this point, we are going to convert the weak pointer into a shared pointer and return the shared pointer.
What would happen if I didn't use that? What would I get?
You get a new reference count.
Yeah, I get double deletion, which would be bad.
That would be bad, yes.
Almost certainly get a crash.
Yeah, I know the answer. I just want to make sure everyone else knows the answer.
All right, so let's pull all this stuff together and see how it all works together, because this is going to actually play directly into almost every pattern you're going to use with the asynchronous I/O library. We're going to create a class of a typical kid. Like typical kids, they cannot walk and chew gum at the same time, but they can talk constantly. Right? There is no way. It's going to have a reference to the I/O service, and notice down here we have our strand. Okay? When we create it, we're going to give it our I/O service so that we can go ahead and hold on to that and use it later. And we're going to, for the strand, we have to give it the I/O service, the HUD that we're dealing with. Oh my goodness. One of us is not working well here. Okay. All right, let's look at walk. Walk is simply going to do nothing except for post that the impl of actually doing the walk. And it's going to wrap that inside of the strand. Because remember, we cannot walk and chew gum at the same time. So therefore, we're going to post our requests to do walks and to do chewing of gum through the strand, and we're going to bind a real implementation to do it. So we have a public interface. This is a pattern you'll probably use over and over again. And as you get the request in, how you're going to handle that, if you can't do both things at the same time, is you're going to post them, and then post them with a strand, and then you're going to get that executed by the butler, right? By your threads. Talk. We can talk anytime we want, so we're just going to talk. The walk impl. It's going to do nothing except for start walking, hang out for 3 seconds, because he only walks 3 seconds at a time, and he's going to print done walking. Chewing gum, we get a flavor at least, and it only takes 2 seconds to chew gum. All right? Let's put this together. So we have our I/O service. This time we're going to go ahead and create a work, just using a shared pointer because we're reinforcing ideas. We're going to create a butler pool. Inside of our butler pool, we're going to have 3 butlers. So we've got 3 threads calling run. Created a scope and a typical kid. Of course, it's Johnny. And we're going to new one of these things off. We're using a shared pointer for Johnny. We're going to go into this loop in which Johnny's going to talk, and he's going to walk, and he's going to talk, and he's going to chew gum, and he's going to talk. And then he's going to wait for 3 seconds. Not because of Johnny, but because I'm tired of hearing him talk. So for 3 seconds, he's going to wait, and then we're going to do that in a loop of 10 times. We're going to leave the beach, which, if you remember right, if we left the beach, and he wasn't in a shared pointer, this would be bad. The butler would try to deliver something to him, he'd get exhausted, and he would die. As I leave the scope, I'm going to call reset on the work shared pointer, which basically gets rid of it, sets it to 0. And then I'm going to join
All the butlers.
All right, so we got created. He starts talking immediately. And you can see start and end walking, which have the pluses, and chewing gum, which have the minuses. They never occur interleave with each other, which is exactly what we wanted. Talking seems to occur all over the place, but the walking and the chewing gum, they never occur at the same time. Make sense? Perfect. All right, we're moving along well. When am I out?
4 o'clock.
Oh, perfect. All right. We only need a couple more things that can I just go over just a little bit? Because I think either the IR is right there or, thank you. We're going to talk just a little bit about a few things you need to know about Asio first, to be able to move forward and then do some communication. As I said earlier, this library is very extensive. There's a lot of stuff in it. And it's one of those things that, if you're like me, you'll just have the reference page open as you're using the library and referring to that a lot. But there are a few things you should know. It has a concept of this thing called mutable and const buffers. Think of them as a pair with a pointer or a const pointer and the size of the thing. Everything's going to deal with memory buffers, right? Memory buffers we just describe as a pointer and some length. In reality, and a mutable buffer can become, obviously, a const buffer, not the other way around. You cannot make a const buffer, obviously, into a mutable. In reality, these things are classes. And they're just going to wrap the memory, the cup, that you own. It also supports scatter gather. If you don't know what that is, then you don't have to worry about it. If you know what it is, then you're probably already concerned about it. If you had a vector or some container, standard container, of these mutable buffers or const buffers, it will perform the scatter gather for you. So it knows how to do that. It understands containers of buffers. Buffers do not own the underlying data. You have the underlying data, you're just wrapping it with the buffer. Make sense? That's really important. If I see any of your handles on IRC asking about that. All right, it's really, really, really easy to get an Asio buffer. Okay, there is a free function called Boost Asio Buffer that has like 27 overloads or something like that. It will create just about anything into a buffer for you. You'll just get the right one. All right, and you'll go to that reference page and you'll make sure that you can get the right one. And if not, it'll tell you what to do to get the right one. All right, that's how you do it. Here are just some simple examples of us here using a socket. We're going to send something. We're wrapping our data and some size with a buffer. Here I have a string. It already knows how to take a string and create a buffer directly out of it. Here I have a boost array. It knows how to take a boost array and wrap that into the right type of buffer. Right? It knows a lot of stuff already how to do it. Standard like vectors and things of that sort of pod types. Just go look. There's lots of stuff. One more thing we need to talk about just briefly is the API. There are free functions such as the async read until you see something, async write. Async read is going to read however much we told it to read. It's going to write however much we told it to write. These are at the shack level, the top level. It's going to make sure all the operations underlying that needed to get done for that complete. Because if you've done network programming, you know that if you tell it to read 1,000 bytes, you likely don't have 1,000 bytes. You're going to get them back in chunks. It's going to take care of that for you. There are also, based on the objects, there are methods. For example, async read sum. It's my favorite. It's going to give you back what happens to be available at that time, which is likely not how much you need, but depending on what kind of operation you're doing, you just start working on whatever you have at that moment. And there's a write sum. All right, let's get going. We're going to now create our Flash XML server. The reason we're creating a Flash XML server is because when this topic, or when the call for papers or whatever went out, literally in like a 2-week period, there were 500 people who said, "How do I make Flash talk with Asio?" So I thought maybe it must be popular. and personally, I do it all the time. So, but it's dead now, so I don't know what I'm going to do. So we have this. We're just going to make a type def to make our lives easier here. This is how I personally want to use it. You might want to use it a different way. I'm going to have a type of this Asio generic server. Serving is something we do a lot of. And serving typically exists of the exact same thing, which is you're going to listen on a port. And when somebody connects, you're going to pass that off to some handler to take care of that client connection. And then you're going to wait for the next person to come and connect to your port. And then you're going to do the same thing. So after a while, you get tired of writing that over and over again, and you just abstract it out. And so I abstracted it out, and I just call it this Asio generic server. It's going to take the type of whatever that handler is, the client handler. And here, I'm telling it I want one thread, but you can have however you want.
So in your generic server, you're assuming this is TCP?
For my server, it's TCP.
Okay, all right.
Yep. Because
Just making sure.
that's what I do
Okay.
a lot. This code's also been munched around and made a little smaller, hopefully, for us to get. I'm going to start the server, and I'm going to give it the port I want it to listen to. I'm going to add a connection handler for, as clients connect, I want it to be able to call something back, which is going to be this XML client connection. It's going to get the handler that has just been connected when that occurs. It's going to take the handler and it's going to add another handler, a message handler. So as it gets messages in, because I should have said this, so Flash, the most convenient way to talk Flash to something else is XML. But it's just the easiest way to do it. And so when you send messages, you send these XML things and they happen to be null terminated, and so you're going to get XML messages out that you're going to get. And that's what I want to process. I want my server just to be able to collect these and use them. And so I'm going to add to that handler that's just connected, I'm going to tell it, this is what I want you to deliver the messages to when they occur. And so I'm going to do something cool inside there. I don't know what it is yet. This thing here for this OMD XML, it's not really XML, I'm sure. And for now, just assume it's like an XML node thing. It does something. All right, let's look at it. So the server class, this is what's going to handle our incoming connections. This one happens to use Signal. We'll talk about that later. And so, how many people use Signal? Okay, just think about it as a way to collect a bunch of handlers that want to be called back later. I can make one call to this functor, and all of them get called back. So,
Publish, subscribe.
it's not yes, publish, subscribe. Pardon? An observer pattern, exactly.
It's unfortunate that the name is Signal, because it really throws everyone off.
I agree. It's going to have some things that are mostly not interesting. It's going to take a thread count. This thing's interesting. We're going to start the server. We're not going to worry about how we're going to stop servers at the moment. We don't have time for that. What's contained inside here is this thread group, because we're going to have however many people we want to work on our beat, or however many butlers we want. Notice now this is a little different. I'm making some assumptions here. I'm not going to take in an I/O service. I'm going to create the I/O service. So for each server that has a port, it's just going to have its own I/O service. There's one slushy hut for each port that you're listening on. That's my design. That's what I wanted to do. And then we have this thing called an acceptor, and we'll get to that here almost in just a minute. Maybe it's not you. Maybe it's just me. All right. Start server. All right. So start server took the port in. What is it going to do? We'll get to this. Well, let's get to this right now. It's first going to new off whatever the handler type was that we wanted. So this is the guy this is going to handle all the communication. And we're just going to new one of these off and hold on to that as a handler. So as a connection comes in, the server's job is just to pass the connection off to the handler. And it's going to take care of client communication. And you'll see this pattern over and over again if you look at the examples too. Connection comes in, we just create an object to handle it, it handles that connection. And now we're going to set up actually the listen. We're going to create an endpoint, and we're going to tell the endpoint what type it is and which port it's going to be associated with. An acceptor does exactly what you probably think it should. It's going to accept connections. We need to tell it what type of protocol to open with. This is the protocol of the endpoint, or in this case, the v4. You can set options on it. I'm going to set the option of reuse address. If you don't know what that is, don't worry about it. It's just standard sockets.
Which apparently is
I'm going to bind the acceptor to the endpoint itself. So I'm going to say, acceptor, you're bound to this endpoint, which is the port at some protocol. And, oh yeah, start listening. Okay, this is similar to what we had before with the timer, and we told the timer to asynchronously start. Same type of thing. And then we're going to start accepts. So now we're going to asynchronously start this accept. When a connection comes in, accept the connection. Handler is going to expose its socket. The one that we created up here, it's going to expose its socket. So we're going to give it the socket, and we're going to bind the connection. We're going to bind the handler. So here's the handler being bound. Handler is going to be passed as, so it's a method of this, and it's this one. The handler is going to be passed as an argument. We're going to copy this, right, by value, which it's a shared pointer. We like that. And then this is like the _1 that we saw earlier, but they're really nice inside the library, and they created a whole bunch of placeholders that represent all the different things that are in the library. And so instead of using and trying to figure out, is this the _1 or the _3, you can just use these. Error. And then we're going to create however many threads that we wanted that are going to service then the I/O service. However many buttons. Are we okay with this? Handle new connection. So remember, this is what gets called when a client connects. So once the client connects, then handle new connection is going to get called. We're going to get the handler, some error code. If there's no error, then I'm going to, whatever this start does on the handler, I'm going to tell the handler, hey, start. Start doing whatever it is you're going to do. This is the magic with signals. We're just going to let the rest of the world know that, that we have a handler that just connected. We're going to create a new handler. This is like bringing a new cup. We're going to create a new handler to handle whatever the next client is that comes in. And we're going to bind, again, ourself this time, right? So we're binding back. And so this is going to just stay basically, it's like Johnny making the request back. The handler is making the request back. All right, let's, yeah.
Just because, why don't we need the last statement?
Because I want to now get the next connection. So if I didn't have this,
nothing else to connect.
There's no more connections that I can accept.
Can I originally somehow register this callback in a way that it will automatically restart?
No.
Nope.
No.
That's
No.
exactly what it is.
That's what this is doing right here. So it's like saying, my timer got done, start the timer again. My timer's done in the handler, start my timer again. I got my new connection. I do the things that I need with my new connection, and I create another thing to take, another object to take the next connection.
And
I bind that in and say, okay, accept the next one.
Well, if it returns void, it could have returned boolean, and somehow...
This is not going to get returned anywhere. This is the butler calling this, right?
The function returns void.
There?
The function returns void.
Yes?
Yeah.
Here?
It could have returned boolean, and the framework would have... depends on what callback once could have decided, oh, callback once re-register itself again.
No.
No.
So the reason it can't is because this is the handler that got called when we got a connection. So we told it, here's the asynchronous thing I want you to do. Accept the connection, and when you get one, let this handler know. The handler is now being told, I have an exception for, and a connection. So now what's that handler supposed to do? I mean, the best you can do is tell the calling thread a return type. The calling thread doesn't care, right? It's completely asynchronous. So if you want something else to get done, you need to do it now. You have to actually set up another asynchronous call here. And so one way of thinking about this is you're going to be chaining these asynchronous calls together to get work done.
So I think basically what he's asking is, if most of the time this is what we are going to do, why the framework is not doing this? I mean, if this is what everybody is going to do, when you get a handle new connection, you pass it up handler, and then you register again.
I think.
Why the framework is not doing it?
Where's it going to go back to?
To the same guy, probably.
What same guy?
You don't know. It doesn't know.
Or maybe
To here? It can't go to here.
Or maybe you can do a close or something.
Well, why don't you just tell it where you want it to go back to, which is what we just did. We told it we want you to accept another. You have to make an asynchronous request, right? There isn't one yet. So we're telling it, here's an asynchronous request.
This is the handler here.
Oh wait.
There's a difference here.
Oh, is this what you're asking about? This one?
No. The difference between this statement, the one that was originally, this is a different handler.
It's the same.
And the
The
function
object's different.
object is different.
This is a different object. It's a different client. Yes, okay. So this handler is going to handle one client. That's it. I got to create another handler to handle another client. And another handler to collect. Because I'm going to worry, that's how I'm going to worry about it.
We can at least refactor this to get rid of the code duplication, right? Between that and the...
Sure.
the other.
Yes.
Yeah.
Yes, you definitely could do that.
Yeah, what you could have done in this case is create a new function, say create and start accept.
Exactly.
Then it's one function and then you call it there. And
We'll see that in the handler.
Actually,
Yes.
so the answer to the question why not return bool is because in IO service run, what actually happens is it just pops off a handler in the queue and calls it. That's all.
Well, it could have done something else.
No, but you're assuming.
But it couldn't do anything else.
So what's happening
so
is.
think about this framework. I mean, it's used for everything from you can register to a directory change with a file handler. You can register serial port I/O. You can register all kinds of different things, right, for asynchronous things. And if you look inside the API, there's hundreds of asynchronous entry points that we can do. Well, what's the default supposed to be for anything?
And remember, you're going to, if you can actually also post a math calculation. So, would you make it return true or false? So you're using a single queue to run all your handlers. So that's the real reason.
All right, this is our itty bitty handler. This is the thing that's going to take care of the client communication. It's got some fluff. This is the signal thing that's going to call back when we get a message in.
Yeah, that's
we're going to be able to create one, give it the service. There's a start that we already saw. It's going to start this thing going, whatever it does. There's some ways to do sending. We can send this, whatever this XML node thing is, or we can send it as a string.
But that's a detail.
And then we can access some different things. Let's take a look. All right. So we had these private members. This time we want to know the I/O service, but we want to know the I/O service, right? So we're just going to have a reference to the I/O service. We created the socket. We own the socket. We're the client. So we're going to have the socket. We actually gave that to the server, if you remember before, to do the listening. A strand, because there are going to be some things that I don't want to happen at the same time. It's going to make my life easier. You can optimize later if you want. So in the constructor, I need to take care of the things that were references. Some more fluff. This is getting the message handler in and the socket return. Okay, back in the generic server, we made this start call. This is all start does. it calls read packet. All read packet does is it starts this asynchronous read until. Remember that? Darn Yahoo Instant Messaging. Everybody mute your laptops and your phones. So this is a free function. We give it the socket. This is like the free function of going to the owner of the shack and giving him the request and the thing and all of it together, right? So it's free. We're giving it the socket. We're giving it here the in packet, where we're going to read things into. It's a read until. I'm telling it just to read until you hit a null. I don't care how you do it, I just read until you get to that point. And then when you're done doing that, this is what I want you to call. Read packet done. Here's our shared from this. Here, then I want to know the error, and I want to know with the placeholder how many bytes were transferred. I'm going to point out at this moment now, this shared from this is being bound. It's being stuck on the async queue of things to get done. That means that I have at least a reference count of 1 to myself. So if everybody else in the world gets rid of me, I don't care, right?
Just do one.
Does that make sense? Okay, you're not going to leave the beach because you have a slushy being made. One word of caution here, because this comes up a lot. Async read until. If you know something about how this data is coming in, it's coming in chunks, okay? You can create a regular expression here and read up to some regular expression or some other thing. It's looking at the chunk of memory that it has, and it's looking at that, and it says, I got what I wanted. It might have more stuff after that. There might be more inside the buffer after the null. But I met the condition, which was read until I got the null. So don't assume that what's inside the buffer is just up to the null.
Yeah.
Because it likely isn't, depending upon what your protocol looks like. You probably have another beginning of a message after that point. And so if you just throw everything away, let's back up and I can show you, this is what in packet is, because I didn't actually say that. It is this thing called a stream buff. It's perfect for this type of application. So it is just another type of buffer that Asio provides when you don't know how much you're reading in. And later, I'm going to take out of the stream up to that point, and then the rest of the stuff's still in the stream, and then I can continue to read following that, right? So I'm not going to lose it.
The delimiter, is it just the character, or can it be anything?
It can be a regular expression.
Yes.
It can be very complex.
In an STD string, who is going to?
There are overloads.
There's a bunch of overloads, yeah. So take a look at the, and it can, if you use my utility, it can actually be a key grammar. Yeah, so we don't have time today. I was hoping that we'd be able to get to it. So for those of you who were in the Spirit discussion yesterday, we talked about the protocol example. So you saw the grammar and you saw a rule, and what I actually have is a utility which I supply a grammar and a rule, and I supply a socket or anything that basically can have an asynchronous thing done to it, so a serial port and whatever, and you just get back your AST. And so how this actually really works for me in real life is the handler gets back the AST, which simply then just passes the AST to the other side in the handler, and so I don't think about it at all. It just brings in serial and it outputs XML. And I hope to give it to you guys someday. All right. Read packet done. So remember we set this up, read until, and what are we going to read until? We hit the null, and when you get that, call this read packet done.
Sorry, what if I want to process the data in chunks myself?
You would do what I normally do, which is read some, async read some, and then you just get what happens to be available at that point, and you just get chunks back. All right, read packet done. If error, do something clever. All right. Clever might actually mean just returning. If we return,
You die.
the handler is done.
No
The
more.
shared pointer will end up having no more reference. The client will get destroyed. Hopefully you're smart enough in your destructor to shut down and then close your socket. That's
Yeah.
the proper ordering to do that in.
Mhm.
And it just all goes away, right? You don't have to think about it.
What happens if I throw an exception inside the handler?
There's nobody to catch it.
Oh, right. Yeah, that's right.
Yes.
Isn't that false? I mean,
Well, actually,
from this
if you
run
run the
statement,
commands, right,
would you be able to catch it there?
at the join point, you get the exception.
Yeah, you would get it at that point.
Where you join it, you get the
But
exception.
yeah, it's gonna get thrown on who knows what thread.
Yeah.
It's one of those
Basically, it's
threads, right?
critical.
Yes,
It's fatal.
Okay. I don't know, I don't tempt fate. So I catch them. Anything that's gonna throw, I catch
right?
inside my handlers, and I deal with it some way. And if it's dealing with it by simply returning so that I just destroy myself, that's fine with me.
You don't know which one,
So that's best I can do for now.
but you still don't.
All right, so here's some of that magic that we won't talk too much about, but we're going to create this something called an XML node, and then we're going to tell it to parse in the data that we got. And now I have an XML thingy, and I can ask its node name, and if it's policy file request, how many people have dealt with Flash before? None of you even care then. It has a whole security model, and you have to tell it back.
Doesn't matter anymore anyway, right?
Yeah.
Anyway,
So it's requesting some policy on whether or not this client's allowed to connect to you or not, and if it does, then you reply back. And I'm just telling everybody. Okay, anyhow. Otherwise, if it's not one of those, then I'm going to update my handler by passing it a shared from this, a pointer to me, so I don't go away, and the packet that came in. At the end, I'm going to call read packet. So that's the factorization that we talked about in the other slide. This is going to start reading another packet. Sending. All right, I've got 2 ways to send. I can either pass it this thing, which becomes a string eventually, or what it's called here, or I can send a string. The string, notice what I'm doing is I'm calling post, and I'm wrapping it inside of my right strand. There are some things that I'm doing internally. I'm going to have a queue of things that I want to write to send out. And I really don't want to deal with the fact that a whole bunch of people can be calling me, different threads can be calling me to send stuff out. So, what I'm going to do about that, I'm just going to wrap it.
Tie it with a strand.
So here's the strand, it gets wrapped, and it's queue message that's being written. Queue message simply looks like this. We start off by checking to see whether the queue is empty or not. That tells us whether there's a write in progress. You'll see that in a moment. We push back the message onto the queue. If there is not a write currently in progress, we start the sends. This normally, if you looked at it, you would you go, oh my goodness, this is going to crash instantly. But it's in a strand, right? So this is perfectly safe. I am guaranteed that queue message is only going to be entered by one thread at a time. They're going to be serialized for me. So going back to the use locks, use strands. They're your friends. It makes all of this really hard stuff easy, because otherwise you're going to have to figure out the hard part of getting things on and off the queues.
What happens if I register for the same event twice? Like read some, read some.
Well, you can do that.
And it's gonna
It'd
read
be
some
like
also.
ordering 2 slushies. So you would read some, and then when that one's done, you've already got another read some.
Okay.
Right? Now, if you had multiple threads, you might actually end up having some problems here.
Yep.
Same with writes.
Yep.
I mean, this seems to be a common problem too. People want to actually just start blasting writes to a socket. You would never blast writes from multiple threads to the same socket in a normal sense. Don't do it in Asio either, because you're going to get exactly what you asked for, right? You've got a single pipe and you're going to be shoving data from a whole bunch of different places down the one pipe, and this is going to become a mungled mess.
But couldn't it be that that's more efficient to have more than one reads? Because your read handler consumes some time, and say you have a UDP connection that you're reading from.
Start another one right away.
Yeah, it
Remember, as
will,
soon as
but-
we call the async, that thing starts.
Yeah, sure, but when in your handler, you do some work, little, but still, if you had another read going on, that could dispatch.
Okay, but so coming into your handler, if the very first thing you did was issue an async read,
That's the same.
it doesn't start when the handler finishes.
So yes, you can do what you're saying, but instead of doing the read at the end of your handler, you schedule the
here.
asynchronous read
Yeah, so this could have been up here,
up here.
and
yeah.
it would have started
Well,
the
after-
next read immediately,
Yeah.
or actually after.
After that,
checking the
yes.
error. We could have then started the next read right away. But the other thing to keep in mind is
your stream.
it's TCP/IP.
Yeah.
The layers at the bottom are already bringing in the data for you. They're coming in, right? The read really is pulling the stuff out by chunks, whatever happens to be available, reassembling it. And we don't care about chunks. We're reading until a certain thing occurs. So I don't know. In this case, you wouldn't get any improvement.
So I have a really stupid question. and
Probably not. It'll probably be really hard and make me
I'll
look
never
dumb.
reveal my ignorance of all things network and TCP/IP. But can you advance to the next slide? There. So you're queuing packets that you want to send, and you're maintaining your own queue. Isn't exactly this what Asio does? That it maintains a queue for you and will send the packets off?
So this is the problem. If we start on a socket, I have a socket, and we start sending information on that socket, and then another thread comes in and starts sending information on the same socket, they're not going to get queued.
Don't walk in front of projection.
We're both going to actually be writing to the same socket at the same time, and we're going to end up with all the data mumbled together.
What?
And so in order to
Started late.
5
to
minutes.
serialize
Alright,
that,
Okay. Well,
we need to queue it, and when one's done, we need to then.
well then wouldn't a write strand
Right strand.
handle that?
Yeah.
Well, that's what I have here.
But then why did you assume it?
So then what's that queue?
What's the queue for?
Michael, what you could do, you could wrap up the message itself with the write handler.
Oh, yes, no, you could have done that.
Then you
Yeah.
don't need the explicit queue.
Yeah.
Exactly.
Mhm.
Sorry, good point, yes.
Okay.
That's true.
Yeah.
And it would change my handler a little bit. And we'll talk at the end maybe how that would change. So something's going to happen here in a second, and then we wouldn't have to do that again. Good question.
XML node, is that a reference up there and same thing as string?
This is being received by const reference?
The one on top, the node, is that a reference and also down a message?
They're both being passed by value.
Oh, they're being passed around.
Yep.
Don't worry about that. It's very likely. Okay, so there, as Eric points out, there possibly is an optimization here. Do we understand what we're doing here, though? Because it'll be important for the next slide.
So the string is passed with value, that may not be like a trait, right? I mean, the string copies.
We won't worry about that. It got only, there's no copies at all. You have to read the website. All right, start packet send. It's going to pop the thing off, or it's not going to pop, it's going to take the thing on the front, the string on the front, it's going to add in our terminator, and it's going to call this async write, giving it the socket, and then here's the free function buffer, and we're going to give it basically the string. It's going to create the buffer for us. Notice we didn't pop it off the queue. That means it still exists. So the Eric method, we got to figure out how to keep our memory existing, because if it goes out of scope, remember this doesn't own it, it just wraps it. So if we had another way to keep it alive, which we probably
Shared pointer.
Yeah, I think it can wrap a shared pointer.
Yeah,
But I
if
don't
you
know
have
that.
a
I don't
write
think that's
connection-
true. I don't think that's true. I'll have to think about that.
The write connection, and your write handler could have that as a member.
But as soon as the right handler took the string and called async write and did this, if that string then went out of scope, which it will,
But you're keeping a shared from this to that.
I'm keeping shared from this, but if the string that I was trying to write was bound to the handler, it's not in the shared from this scope, right? It's going to go away.
But you can wrap the buffer in a shared pointer and supply that to packet send done.
But the buffer in a shared pointer doesn't help me because the buffer doesn't own the data.
Yeah.
Your own buffer.
Right, I can make all
the
kinds of
queue-
other things, or
the
just
queue
make a
is-
queue like I do.
Yeah.
For me, that was the easy solution. Oh, and then the handler here is packet send done. All right? Packet send done, if there was not an error. At this point now, we pop the thing off the front, because we don't need it anymore. Away it goes.
Marshall?
End of the tape.
Please.
That's great, it's almost the end of the discussion. How's that?
1 minute.
Go ahead. I got 5 more minutes.
Okay.
Michael?
Yes.
Are you sure that you're popping up the right thing from the front?
Yes, because I pushed back.
I mean, you're passing the reference in the first element to the spread.
So when I receive them, I push them onto the back of the queue. When I process them, I use the one that's on the front of the queue.
When it's done,
When it's done,
You
it gets
pop the
popped
front.
off the front of the queue.
there's only one way.
There's no way they're going to get out of it. It just won't happen. Unless you believe in all that stuff from the talk yesterday. Then I don't know what's going to happen. Something else. And then if there's some error on the SYN, we could do something clever down here. And so in here, so we're going to pop it from the front. And remember, we're the only person looking at this queue because it's in a strand. We're going to check and see if it's empty. If it's not empty, we've got something else to do, and we can start the send again.
Yep.
By starting the send, we're going to start another asynchronous thing happening, which is going to get a shared from this bound to some handler, and we're going to continue to stay alive as long as we have asynchronous stuff and handlers. But as soon as we run out of those,
You're gone.
we're gone, which is exactly what we want, right? We only want our client object to stick around as long as things are great and we're working with the asynchronous I/O. Okay. Did all that make sense? All right. This is the end. Couple words here. We were just in this example. What we were doing is we were just calling some handler that did some stuff. From our earliest examples, when we had the timer going, we know that if we call a handler and it's taking a really long time to do something, nobody else is getting their slushy served. Right? That could be a problem depending upon your application. If that's true, in your handler, a really simple way to take care of this is you can have another I/O service and you just post work to get done. So it does nothing more than takes the callback, it binds some work, right? The actual function that you want to have process the data, and it sticks it on. So now we have two I/O services. We have an I/O service that's handling our I/O, and we basically have a thread pool that's doing our calculations or whatever it happens to be. That's like a real simple way to handle this problem of blocking when you have I/O occurring in some long operation. All right? Is that hand? Or, okay. Next word of advice. I use signals. Really what you want to do is use signals too. So if you have a situation that's very similar to this, where you have handlers that want to know information that's occurring, signals is the way to go. And signals too is really the way to go, because it handles all the threading headaches that occurs with connections and disconnections. When it says that signals 2 is thread safe, that's what they're talking about. They're not talking about all the stuff that you might hope. They're talking about the connection handling of connecting in a handler and removing that handler, or what if the handler goes away and you didn't know about it, or what happens when somebody comes in and another one tries to connect at the same time. All those problems that you have to deal with multiple things connecting or disconnecting, it takes care of. So Signals 2 is the way to go. The final thing, use strands. Strands will help you in all kinds of situations. When you're starting to write these things and you start to look at it and it's becoming complicated and you start having locks and you start having all kinds of other weird things going on and the problem looks hard, just step back and say, all right, that must mean that I have things that can't be happening at the same time. Let's use a strand or multiple strands to make sure that those things will not happen at the same time. All right, that's it. Okay, yeah, actually that's a good question. So the presentation will be up. I'll send it to her. It's my fault. And yesterday's also will be up. And as I mentioned yesterday, the code for all of yesterday's Spirit stuff, all the code that's in for this is all set up in little compilable test programs with a jam file. And how I recommend is you just take the tarball, unzip it inside of the Boost 143. It'll create something called Boostcon. Go inside there, just type in bjam, and then everything will just work. Okay? And then you'll have all these examples to play with and do whatever you want. All right.